as he just said, I'm representing Luxembourg. I'm doing my PhD at the University of Luxembourg. I'm going to talk about robust estimation in finite state space, hidden Markov models. Can you go to the next slide, please, Andre? So I'm going to briefly try to introduce hidden Markov models, and then I will try to present our method or our strategy, and then give results. And somehow our method is not very specific to hidden Markov models. So if I have time, I will also give another example for which we can apply our method. Thanks. So next slide, please. Again. Yeah, so this is a simple representation of a hidden Markov model. This is a homogeneous Markov model. So you can characterize them. It's a bivariate process HI, XI. So on my slide, HI is the hidden process. It's the hidden Markov chain with initial distribution pi and Markov kernel Q. And XI is the observations. And at times t, xt depends only on ht. And it follows a distribution f of ht. And so the Markov chain H belongs in a space that could be called, like, I don't know, calligraphic H, and this is called the state space. And in this talk, I will only focus on finite state space. So it means that the Markov chains can only take finite values, in my example, from 1 to k. And then what you want to estimate in general is the different parameters. So the initial distribution of the Markov chain, it's well, in this case, the transition matrix, and also those distribution f of h, fh, that are called emission distributions. Yes. Next slide, please. So hidden Markov models are applied in many different areas, and it's if you know already mixture models, it's like a step forward when you include the dependencies in your observation. So main examples of voice activity detection, climate state identification, automatic speech recognition, facial expression recognition, and also to work on proteins. And well, it does even more examples in many different areas, economics, finance, or even natural sciences. And for people, it's very important to estimate those parameters because they also have like usually some meaning for them. Next slide, please. So there are some existing results. I'm mentioning the most important one that was established recently, 2018, I think. And I'm explaining the type of result they get and how they get it. So what in this paper, LRAC, they provide non-asymptotic results in a non-parametric context, and with also including the selection of the order k. This index k is just the size of the state space, so the number of hidden states that the Markov chain can take. Next slide, please. So, and the idea behind that is just that if you look at the distribution of consecutive observation, so in this case, L consecutive observation, and you actually observe in a stationary hidden Markov model, well, you can deduce the parameters from this distribution. So in their framework, they prove this type of inequality, which says that if actually the density related to this distribution, if such densities are close enough in terms of the L2 distance, then the distance between the different parameters will be also small. And so next slide, please. And then the idea is just if you can deduce an oracle inequality for the estimation of this density, of L consecutive observation, then you can deduce a similar result for the estimation of the parameters. And because they also want to do the selection of the order K, they just use a penalized least square estimator, and they use model selection results to prove that they can estimate it correctly with high probability. And then because this inequality, this lower bound on the L2 distance between densities is only valid if you have the right order. So they first show that they can estimate correctly the order, and then they can say that they also have like an oracle inequality for the estimation of the parameters. Yeah, basically that's it. And so in my case, I want to focus on robust estimation. So here I'm trying to explain what I'm aiming for. So basically, in general, what you have is you have data, you have a model, and your estimator should be something that belongs to your model. So if you believe you have your observation come from a Gaussian, well, your estimator will return a Gaussian or an estimate parameter of it, for instance. And usually people assume that the true distribution of the data belong to the model. In that case, I don't want to do that. I don't want to assume the true distribution is a hidden Markov model. I just want to believe that my model can be a good approximation of the true distribution of the data. And I want to put, if I have restrictions that I need to make, I want to put them on the model and not on the data. I want to assume as little as possible on the data because, well, you can never check in practice your assumption on the data. So you want to make kind of realistic assumptions on the data. And then what I also want to have is non-asymptotic deviation bounds that are also easy to understand. And also when the situation is ideal, so when the distribution of the data actually belongs to the model, you want to have convergence rates that are, well, minimax or at least close to it. And I want also to be able to show that the estimator is robust to outliers or contamination. Yes. And so the approach here is that first to notice, well, if you're not familiar with it, but you don't know it, but you should take it for granted that finite state space hidden Markov models or mixing, or like unless very rare occasions, they are mixing. What does that mean is that, for example, if you take the random variable xi and the random variable xi plus k, and you take k that goes to infinity, they are almost independent. So if you're familiar with beta mixing, alpha mixing, finite state space hidden Markov models satisfy all those mixing conditions. And the idea is that, well, this is really informal. They are all the observations are independent with high probability. Next, please. And then, so the idea is that maybe we can use some methods that has the property I explained I wanted in the last slide, but only for independent observations. And the idea is we'll try to be, since the observations are almost independent, maybe I can show that it's not a problem that we have this dependency in a way. So I will use row estimators that have been developed by Yannick Baron, my supervisor, also with Lucien Berger and Mathieu Sarr. And those estimators are proven to be robust and to have the desired properties for independent observations. And then the idea is to use that is to get a subsample, or actually more like a subset of the observations that would be like as independent as possible. So like to artificially create an independent set of a set of independent observations, and then use that to use the theory already existing. And next, please. Yes. So now I will try to explain deeply, well, more clearly the methods that I use. How do I do this? What I just said, like how to create a subset of observation that is the most independent and how it works in practice. And next, please. So, well, this looks a bit difficult to understand, but it's clear. So as I explained earlier, and I'm building on also the result already existing, you can deduce the parameters of the hidden Markov models from the distribution of L consecutive observations. So here the idea is like I will take the first L observations, and then because I have a mixing property, I will not use a number of observations after that, here S, and then I will take another block of L observations, and I will, well, here they are written Y1, 2, 3. And those are the observations I get at the end of this subsampling process. So the blocks of length L is because, well, I want to estimate, the intermediate step is to estimate the distribution of L consecutive observations. And those unused block of length S is to try to use the mixing property to get like independent observations. So here, if S is very large, Y1 and Y2 should be almost independent. So that's what I write below. I have like this distribution P star S. This is the joint distribution of this new set of observations. And then there's what I called P independent S, which is like the product of the marginals, which would be the true distribution of those distributions if they were truly independent. So in a way, to measure the dependency between these set of observations, I can look at the distance between those two distributions. And so this is the deviation bound I get. So here, well, I need to explain everything basically. M is the model I'm building the estimator on. And so H is the Hellinger distance. So if you're not familiar with it, is the L2 distance between the square root of the densities. But then what's nice is that you don't need, for example, a condition of square integrability, and convergence with respect to the Hellinger distance is similar to the convergence with respect to the total variation distance. So if you don't know the Hellinger distance, just think of it as the total variation distance. And so we have Pi is the distribution of the block I, Yi. And so ideally, the process is stationary and they all have the same law. And if they have this, well, distribution PL, that would be the distribution of consecutive observation, you will have NS times this distance between your estimator and the target distribution. And so this is upper bounded by 3 different terms. Can you go to the next slide, please? Yeah, so the first term is the approximation term, and it measures how far the model is far from the true distribution of the data. So in the case of when the Pi are all equals to, let's say, a small P star that belongs to the model, this term is equal to 0. So when you make the assumption that the true distribution belongs to the model, this term goes to 0. The complexity term measures, well, yeah, the complexity, how big your model is. And there's the dependency term. So here is the Kullback-Leibler divergence from the joint distribution to the product of the marginals. And this term is also equal to 0 if your observations are independent. So in a way, in the perfect situation where everything is independent and IID, you only have the complexity term left, and this will give you a convergence rate over the model. And here the idea is that the approximation term and the dependency term are, well, they account for some kind of robustness. So the approximation term accounts for how far you can allow the distribution to be not exactly in the model, and the dependency term, it allows to deal with observations that are almost independent, but not exactly independent. And so the idea here, for me, if for one moment we do as if the approximation term is 0, would be to balance the complexity term and the dependency term. Because when I take S very large, the dependency term will be low, but then the sample size will be very low as well, which is bad. And so then the idea is like, how do I balance them? And to do that, I have to do something else. Can I have the next slide, please? So yeah, first this bound is assumption free. So as I said, when I make more assumptions, I can bound the different terms and make it a bit more meaningful. But then also, next slide, please. Yeah, so as I said, here DKL is it's a mistake, it's a typo, is the callback library divergence as well. To know how to choose S, I need to know the behavior of this dependency term. So then this needs to be investigated, at least in the case of finite state space hidden Markov models. So can we go to the next slide? Again, so now what are the results when I look at hidden Markov models? Next, please. So this term is very complicated, but then when you work with Markov processes, it becomes much simpler. So here, this is the callback linearization between the joint distribution of my different block of L consecutive observations and the product of the marginals, and it can actually be just upper bounded by the sum of here you can see that it's the distribution of H. So H is the Markov chain that takes only finite values, and it's only two different. And here, like the indices, it becomes like this is the HI plus S is the highest indices in my block of lengths L in corresponding to YI. It's a bit complicated with the notation, but like basically we have a trick to have a simpler notation, and this H is like Markov chain on a finite state space. So this can be bound in a way easily. Next slide. And what we get is like if it's if it has a translation matrix Q that is irreducible and aperiodic, then we have those two inequalities. Basically, we have ergodicity, but here not as you usually see it. But it just tells you like all the two different terms, they decrease geometrically fast. And so you can do, well, the first one tells you that you can bound this dependency term in a certain way with respect to S. Here you have K, but if you replace it with S, you have the same thing. And the second one tells you that also, like, even if the Markov chain is not stationary, you don't really care because it's going to go, you can do almost as if all the observations were P star. Okay, next slide, please. So yeah, that's what I just said. We'll just, like the first one on the left is the mixing, and the second one tells us that we don't need to make the assumption that it's stationary. Okay, and then we get the main results. So the model I have here is, well, it's just how you would write the distribution of L consecutive observation for a finite state space hidden Markov models. Here I take emission distribution in this class of probability distribution capital F, and yeah, so when this class of distribution is exponential family, I get the risk bound as below, and here you can see that so P star is just like this distribution I get from ergodicity of the hidden chain. And so this is basically what I want to estimate. And I get this risk bound. And so the first time is the distance from, well, this P star to the model. And the second one is like I have balanced the complexity term and the dependency term here. So yeah, I have like the K is the order and L is the number of observations. I have the dimension of this class of probability F, and I have a additional logarithmic term. And well, this is minimax rate up to the logarithmic term. And also this required well, this R to be known, which was from that depends on the true transition matrix Q. But then even if it's a no, I can take S a bit larger and get still a good rate. I just have a worse logarithmic term. So I guess I don't have time to give the last example, which was to show that we can do something similar, but when we look at the diffusion process, well, discretely in time, we can use the same thing to estimate the invariant distribution. So yeah, and here there's also a slide to show that it's robust to, well, something that I call independent contamination, but if I don't have time, it's just to look at contamination and outliers, but to handle it with the fact that the observation on R dependence. Yeah, so I think that I'll stop here. Thanks. Yeah, thanks a lot, Andre. And those are yeah, the references I used in the talk.
Okay, thank you, Alexander. So we have a few minutes for questions. Are there any questions from the audience? So maybe I can start with one. So in slide 7, I think you had Andre, if we can go back to, yeah. It was yes. So yeah, so actually my question was more, yeah, okay, slide 7, but then related to your general results. So here you have this universal constant. So I have kind of two questions. One, if you could give an intuition of what does this constant depend on? I guess something related also to the model that you choose, but
no,
then,
actually, the idea is that this constant is universal, so it doesn't depend on anything. But if you really want to have the best constant, it's not great because here I want to have robustness and I also want to have something universal. So the constant is way too bad to have the optimal constant.
Okay. And this is the same constant that comes in also in your general results, which is at what is it? Slide 10, I think it was. It was a bit later. One back, I think. No. Yeah. So here you have this constant C is again related to that, or the first one.
The first C is universal. Yeah, I didn't have time, but the first C is universal, at least in the context of those hidden Markov models. And the second one depends on the true transition matrix. If there is a true transition matrix, it's there. But I mean, so this is if it's a true finite space hidden Markov models, not the cylinder model. But if it just has a mixing property, there's a constant in the mixing bound, and it would depend on this constant.